Welcome to the debate, manufacturing speed. Can massive industries actually move fast? Today, we analyze the ideas from the book, The Agile Blueprint. Imagine finding a critical design flaw in a surgical tool just as you're preparing for mass production.
Terrifying.
Right? In 1995, that discovery would have cost you $1 million in scrapped steel molds and, basically a year of your life.
Yeah, total nightmare.
But today, you can supposedly print a new functional prototype by lunchtime. But is this rapid reality actually scalable for heavy legacy industry? That's what we're tackling today. We are looking at a central premise that is keeping executives up at night.
Oh, absolutely keeping them up.
The idea that rapid prototyping and agile manufacturing are no longer optional strategies. They are supposedly absolute existential requirements for modern production.
Which is a huge shift.
It is, because these legacy organizations are caught in this brutal paradox. On one hand, they need meticulous, zero-tolerance precision. But on the other, they are facing this uncompromising imperative for breakneck speed. The claim here is that they must choose between rapid adaptation or total obsolescence.
Adapt or die, basically.
Exactly. But look, as the skeptic in this discussion, I really have to ask, is this realistic? What are the actual on-the-ground risks of doing this? Does a systemic overhaul actually work in the long run? Because from my perspective, massive legacy industries are structurally rigid for a highly rational reason.
Well, they're built to last, sure.
Right. When we talk about industrial manufacturing, we are talking about immense capital costs, harsh material limitations, severe scalability bottlenecks, and frankly, terrifying intellectual property risks.
I hear that, but
Just to finish the thought, proposing that a century-old manufacturer suddenly pivot to agile methodologies, just ripping up their established supply chains to adopt a Silicon Valley software mindset, that seems like a highly risky proposition for a widespread systemic overhaul. These systems were built to be deliberate because, a failure in heavy machinery isn't a software bug, it's a catastrophe.
Look, I understand the instinct to protect those established systems. I really do. But I am firmly in the camp of the believer here. I fundamentally trust the transformative power of these agile methods because, honestly, the alternative is just a slow march to irrelevance.
Irrelevance? That's a strong word for multi-billion-dollar industries.
But it's true. The traditional linear, sequential manufacturing model is it's a supertanker. It's massive, it's impressive, and it takes 5 miles to turn around. In today's market currents, a supertanker is doomed to stall out on innovation.
So you just strap a speedboat engine to it?
No. By utilizing iterative, parallel cycles and integrating early-stage validation through rapid prototyping, these strategies do something incredible. They drastically lower the cost of change, and they comprehensively de-risk the entire innovation process.
De-risk? By moving faster?
Yes, exactly. We are no longer waiting until month 8 of a 12-month development cycle to find out a part doesn't fit the assembly. By leveraging advanced manufacturing, we are testing physical realities in week 1. It's not about acting recklessly. It's about learning so fast that failure becomes a cheap, routine part of finding the perfect solution.
Okay, I hear the theory, but let's apply that to the balance sheet and the actual factory floor. Let's look at the financial and operational realities of what we might call this prototyping paradigm.
Sure.
The argument is that moving from sequential development to accelerated feedback loops allows companies to test form and fit immediately. But how does that actually manifest when you're dealing with heavy industry and not just, cheap consumer plastics?
It manifests as raw survival. The logic behind the prototyping paradigm isn't just about printing a plastic widget for a boardroom presentation. It's a philosophical shift toward relentless refinement.
Relentless refinement?
Right. In a traditional sequential model, each phase must finish before the next begins. You design, then you engineer, then you tool, then you manufacture.
Which makes sense. You need to know what you're building.
But if you find a flaw at the tooling stage, you're bleeding capital. When you introduce rapid, accelerated feedback loops, you are testing physical, tangible hypotheses almost instantly. Take that MedTech innovator case study.
The surgical tool.
Exactly. They were designing a novel, minimally invasive surgical instrument. In the old model, each physical iteration required machining parts from scratch, taking months.
Sure.
But by bringing in high-resolution stereolithography, or SLA, and multi-material jetting, they completely changed the physics of their workflow. And let's be clear on how SLA works. It uses a highly precise ultraviolet laser to cure liquid resin layer by layer into a solid, isotropic part.
Right, it's highly detailed.
Because of that technology, they didn't just speed up a little. They iterated 20 times faster.
20 times?
Exactly. And the mechanism of why that matters is crucial. Because they could use SLA to hand a highly accurate, functional prototype to a surgeon within days, they received immediate tactile feedback.
So the end user actually gets to touch it?
Yes. The surgeon could literally hold the instrument and say, this grip is too wide for my hand during a delicate maneuver, and the engineering team could revise the computer-aided design, the CAD model, that exact afternoon.
That is fast, I'll admit.
They shaved an entire year off their launch timeline and cut their development costs by 30%. That is the power of parallel development. You are mitigating risk through early learning rather than extensive, paralyzing upfront planning.
Okay, that works in a vacuum, sure. But look at the friction when we scale this up to the macro level of massive industries.
What friction?
Well, a med tech device that fits in the palm of your hand is one thing. But moving a legacy industry is like turning that super tank we mentioned. Rapid prototyping is touted as a speedboat engine. But strapping a speedboat engine to a supertanker doesn't make it agile. It just burns capital.
I completely disagree with that analogy.
Let me break down the operational model, because I really have to question the long-term reality of these upfront costs and the scalability. If an enterprise decides to build this capability in-house, the initial investment is astronomical.
It's an investment in the future.
But we aren't talking about desktop printers here. To get end-use functional metal parts, you need direct metal laser sintering, DMLS. That process involves spreading a micro-thin layer of fine metal powder and using a high-wattage laser to melt it into solid metal.
Which yields incredible strength.
An incredible cost. Or you need multi-jet fusion, MJF, for production-grade polymers. You're looking at millions in equipment, plus specialized HVAC systems to handle hazardous powders, facility retrofits, and entirely new software ecosystems.
But the alternative is stagnation.
Let me finish this thought, please. Because the alternative pathway has its own massive flaw.
Okay, go ahead.
If you flinch at the capital expenditure and decide to outsource to external service bureaus, you are now transmitting highly sensitive proprietary CAD files over external networks. You are literally emailing the digital blueprint of your company's future to a third-party print farm.
That happens every day in manufacturing.
But not with your core intellectual property all in one neat printable file. So you either bleed cash up front to build an internal lab that might sit idle while your engineers learn how to use it, or you risk your IP to save a buck. Does this actually work in the long run for a company producing heavy machinery?
I'm sorry, but I just don't buy that binary framing. You are presenting a false choice between bankruptcy and corporate espionage.
It's a real choice for CFOs.
Let me tell you why it's not. You don't strap the speedboat engine directly to the supertanker on day one. You use a phased implementation roadmap. The strategic approach is to pilot and learn.
So you dip a toe in.
Exactly. You do not start by dropping $5 million on a DMLS metal printing farm and a hazardous material handling facility. You start by validating the return on investment with vastly cheaper technology, like fused deposition modeling, or FDM, the plastic extrusion stuff.
Right, FDM. It essentially acts like a robotic hot glue gun, extruding melted standard thermoplastics like PLA or ABS, layer by layer to create quick conceptual models and early functional manufacturing jigs.
But hold on, FDM doesn't give you the material properties a legacy manufacturer actually needs for end-use testing. A plastic jig doesn't tell a heavy equipment manufacturer how a part will perform under 10 tons of shear force.
It doesn't have to test the shear force yet. It gives you geometric validation and spatial awareness for pennies on the dollar.
You run a pilot project, something low risk but highly visible on the assembly line.
Okay. You build a cross-functional team, you apply FDM rapid prototyping to that specific pilot, and you gather immediate feedback on form and assembly fit. Once that printer proves that you can catch a geometric design flaw in week 1 instead of month 6, you've justified the investment to the board.
And then what?
From there, you scale and integrate. You move up to the expensive metal systems or production-grade polymer systems only when the workflow and the culture are ready to absorb them.
And the IP issue?
Robust non-disclosure agreements, end-to-end encrypted files, and secure digital rights management protocols are standard practice now. The risk of a rogue service bureau stealing your CAD file is frankly lower than the risk of a competitor beating you to market by a year because they iterated faster than you.
All right, fine. Even if a company solves the capital hurdle and acquires the machines, let's say they successfully navigate your pilot phase, the true bottleneck just shifts from the finance department to the engineering floor.
How so?
Because the structural reality of implementing this is brutal. Taking a part designed for traditional injection molding or CNC machining and just, throwing it into a 3D printer is a recipe for disaster.
Oh, completely agree. I 100% agree. And that's exactly where the magic happens.
Magic?
Yes, we're talking about the transformative power of design for additive manufacturing, or DFAM. This is where we stop just making things faster and start making things that were previously impossible. DFAM fundamentally breaks traditional manufacturing rules.
By introducing extreme complexity?
By introducing optimized complexity. Think about the mechanism of topology optimization. Instead of a human engineer guessing where a part needs to be thickest, we use finite element analysis algorithms.
Letting the computer design it?
Basically. The software analyzes the exact load conditions, the stress factors, and the anchor points a part will face, and it automatically strips away all non-essential, non-load-bearing material. You end up with these incredibly organic, almost bone-like structures that offer the absolute maximum strength-to-weight ratio.
They do look like alien artifacts, I'll give you that.
Or consider lattice structures, internal repeating geometric patterns. In traditional manufacturing, a block of aluminum is solid. With DFAM, you can design a part that is solid on the outside, but filled with a tailored lattice on the inside to absorb impact or manage thermal conductivity.
But is that actually practical?
Look at the Aerodyne Aerospace example. By utilizing selective laser sintering, or SLS, where a laser fuses nylon powder into complex shapes, they redesigned an engine component to feature these intricate, lightweight internal geometries.
Right.
The result was a 15% reduction in weight and a 20% improvement in fuel efficiency. In aerospace, where every ounce costs money to put in the air, those numbers are earth-shattering.
That is a brilliant theoretical design, but we have to look at the operational friction of actually producing those complex geometries at scale. Does part consolidation truly simplify the supply chain, or does it just shift the bottleneck from the assembly line to the printing bed?
It simplifies it.
I'm not so sure. What about the intense manual labor of post-processing? We talk about rapid prototyping, but there is nothing rapid about post-processing. Let's look at the material limits and the chemistry of what you're proposing.
Okay, let's look at it. You mentioned FDM earlier as a starting point. PLA plastic is biodegradable but incredibly brittle, right? It snaps under minor stress. ABS plastic is durable, but it works notoriously if the thermal environment in the print chamber isn't absolutely perfect.
Those are just the entry-level materials.
But even if you move to resins with SLA, you get beautiful detail, but the parts are inherently fragile. They degrade under ultraviolet light, and they require highly toxic chemical baths, isopropyl alcohol washes, and specific UV curing ovens just to finalize the polymer chains.
That's just standard processing, but it takes time. Even with your ultimate goal, metal DMLS, you are literally welding metal powder to a build plate using a high-powered laser. Gravity and thermal stress mean you have to print solid metal support structures underneath overhangs.
True.
You can't just snap those off by hand. You have to send that printed part to a traditional CNC machine shop to have those welded supports milled away, then heat treat it to relieve internal stresses and manually sand it. So yes, you consolidated an assembly of 10 parts into one printed part, but now a highly paid technician has to spend 2 days manually processing that single item. Where is the practical efficiency in that?
That's a highly detailed critique, but it assumes we are stagnant. True agility means designing specifically to minimize those exact hurdles. You are describing a scenario where someone is using the wrong technology for the geometry or failing to design for the process.
I'm describing the reality of the shop floor today.
But if support removal in metal is your bottleneck, you change the orientation of the part during the design phase so it doesn't need overhang supports. If we are talking polymers, you transition to SLS or MJF, multi-jet fusion.
Which use powders.
Exactly. Because those technologies operate inside a dense bed of polymer powder, the uncentered, loose powder itself acts as the support structure for the part being printed. There are no breakaway supports. You pull the part out, blast away the loose powder with compressed air, and it's practically done.
Come on, the surface finish on SLS is porous and rough. And managing huge vats of airborne nylon powder is its own hazardous headache for a facility.
It's a solvable operational process. It requires basic industrial ventilation, not a systemic failure of the method. And the payoff is immense. You mentioned part consolidation shifting the bottleneck. I argue it eliminates the bottleneck entirely.
Eliminates it.
Yes, by consolidating dozens of traditional components into a single print, you are removing fasteners, you are removing rubber seals, you are completely eliminating tolerance stack-up issues, where tiny errors in 10 different parts add up to a final assembly that doesn't fit together.
Okay, fewer parts, fewer assembly steps.
Exactly. You are fundamentally making the product anti-fragile. An assembly with 50 bolted parts has 50 potential points of failure, 50 inventory SKUs to manage, and 50 supply chain vulnerabilities. A single, topologically optimized printed part has 0 assembly joints.
Sure, structurally it's sound.
It thrives under stress because it was algorithmically grown to handle that specific stress. We are moving from resisting failure on an assembly line to designing failure out of existence in the software.
If part consolidation changes the physical assembly, the introduction of AI and dynamic materials changes the very nature of the product itself. And this is where we move from what we can realistically print today to how systems will supposedly operate tomorrow. And frankly, this is where I think the narrative loses all touch with the factory floor.
We have to look to tomorrow because the horizon is approaching exponentially fast. The logical extreme of this agile blueprint is breathtaking. We are moving toward multi-material printing.
Which is,
Imagine a single print cycle where multiple print heads deposit rigid structural polymers, flexible rubber-like hinges, and even conductive silver traces for internal electronics, all simultaneously.
which is incredibly experimental and prone to cross-contamination.
It's currently in advanced R&D and bleeding into high-end manufacturing. But beyond that, we are looking at 4D printing. This introduces time as the fourth dimension. We are talking about materials that are programmed at a microscopic level.
Oh, wow. So they change over time?
Yes. Imagine a flat polymer joint that is engineered with internal stress gradients. So the moment it is exposed to ambient humidity or a specific temperature shift, it autonomously swells and folds itself into a 90-degree angle.
That sounds like science fiction.
Combine that self-assembly with AI generative design, where artificial intelligence doesn't just optimize a human's design, but autonomously runs finite element analysis on millions of permutations overnight. It invents solutions human engineers wouldn't even conceive.
I mean, that's theoretically fascinating, but
Ultimately, this creates a network of localized, self-optimizing digital manufacturing nodes. If there's a global supply chain shock, a canal blocked, a pandemic, it doesn't matter, because you don't ship physical parts anymore. You route the digital file to a local node and print the exact optimized part on demand.
look, if you're listening to this and running a mid-sized machine shop, you're probably rolling your eyes right now. You're thinking, I can't even get my CNC machines to talk to my ERP software, and you want me to invest in self-assembling biopolymers.
It's where the industry is heading.
Are we distracting these mid-sized industrial manufacturers with sci-fi concepts like 4D self-assembling materials when they are still struggling with basic legacy machine downtime? Seriously?
A mid-sized manufacturer is trying to figure out why their supply chain management software isn't integrating with their accounting department.
That's a fair point.
And we are telling men to bank on AI-driven generative design. That is a massive overreach for a company that is just trying to get a viable, functional prototype out the door without busting their quarterly budget.
It's not a distraction, though. It's a trajectory. Fixing your ERP to build outdated products is like putting a state-of-the-art GPS on a horse and buggy.
That's a bit harsh.
But it's true. You know exactly where you are, and your accounting is perfectly synced. But your competitors are still going to outpace you. You don't have to implement 4D printing today, but if you don't understand that your competitors are building the digital infrastructure to eventually leverage it, you are already obsolete.
So they have to start now.
Yes, and the AI-driven design isn't sci-fi. It's available as a cloud plugin in commercial CAD software right now. You input the load parameters, the material constraints, and the manufacturing method, and the software gives you the optimized design.
Okay, the software is here. I'll concede that.
The point of discussing the future horizon isn't to intimidate the manufacturer, it's to illuminate the ceiling of this technology. With traditional manufacturing, the ceiling is known. It's rigid, it requires expensive steel tooling, it hates change. With the prototyping paradigm, the ceiling is constantly expanding.
Right.
Once a company gets a taste of iteration speed, once they see a physical part in 24 hours instead of 8 weeks, the entire cultural mindset of the company shifts. They stop asking, how do we make this cheaper to machine? And start asking, how do we make this perfectly optimized for the end user?
I hear the theory of that mindset shift, but let me apply some friction to it. A culture of continuous iteration can very easily become a culture of perpetual tinkering.
Tinkering?
Yeah. If the cost of change is practically zero, what forces an engineering team to actually commit to a final product? I've seen it happen on design floors. Because it's so easy to just hit print on another version, engineers will run 20 iterations, tweaking a millimeter here and a degree there. They burn the time they theoretically saved, all while the market window closes.
That's a management issue, not a technology issue.
But traditional manufacturing, for all its faults, forces discipline. You have to be absolutely right the first time, because cutting the steel for an injection mold costs a fortune. That fear produces rigorous, highly deliberate upfront engineering.
I'm sorry, but I just don't buy that fear of a massive bill is the best driver of engineering excellence. Fear produces conservative, incremental designs.
It produces safe designs.
It produces parts that are heavily over-engineered, thicker and heavier than they need to be, simply because the engineer added a massive safety factor to avoid the catastrophic career cost of a failed mold. The discipline in agile manufacturing doesn't come from fear of tooling costs, it comes from rigorous, data-driven validation.
Validation takes time too.
But it's empirical. You aren't just tinkering for the fun of it. You are printing a physical part, testing it against real-world mechanical criteria, gathering empirical data, and iterating based strictly on that data. That is a far superior scientific form of discipline.
And yet, we always circle back to the physics of the materials. We can talk about data-driven validation and software magic all day, but if you need an engine part that can withstand 500 degrees Celsius and constant mechanical friction, a polymer printed on an MJF machine is going to melt into a puddle.
Obviously, you wouldn't use a polymer there.
And a metal part printed on a DMLS machine is going to require extensive traditional post-machining to achieve the necessary surface tolerances for a frictionless seal. You end up marrying the rapid prototype back to the legacy machine shop anyway. The supertanker still has to carry the load.
But hybrid manufacturing is absolutely a valid and highly effective strategy. Taking an additively manufactured metal part that has a complex internal cooling channel which could never be reached by a conventional drill bit, and then clamping it into a 5-axis CNC machine to finish a critical mating surface is the best of both worlds.
So you admit you still need the old machines?
Of course. You get the internal thermodynamic complexity of 3D printing and the extreme surface tolerance of traditional machining. That isn't a failure of agility. That is the definition of leveraging all available tools to create an uncompromising, superior product.
Well, we're coming up on time, and I think that tension between the sci-fi future horizon and today's factory floor is exactly where we need to leave this. Let's step back and look at the final verdict on the core ideas from the source material.
Sounds good.
From my perspective as a skeptic, the hurdles of scaling this technology, the massive facility retrofits, the severe IP risks associated with external service bureaus, and the hard chemical and physical limitations of additive materials all require strict, unforgiving scrutiny.
Fair enough.
Overhauling legacy systems with these methods is not a guaranteed path to salvation. It is a complex minefield that demands a highly cautious, heavily analyzed approach to capital allocation.
And I maintain that while caution is necessary, inaction is fatal. The agile methods we've discussed provide a necessary iterative engine for continuous innovation.
The engine of survival, you said?
Absolutely. By embracing parallel development, design for additive manufacturing, and rapid physical validation, companies are not just making parts faster. They are fundamentally building resilient, anti-fragile operational systems capable of surviving the chaotic modern market.
Which brings us back to our final filter on the material. Looking at the methods and DFAM principles proposed in the Agile Blueprint, we have to ask, is this a must-try for immediate survival in modern manufacturing or an experimental frontier that should be approached with high caution and phased capital allocation?
It is absolutely a must-try. The technological barrier to entry has never been lower, and the cost of ignoring it has never been higher.
It remains an experimental frontier for heavy legacy industries, requiring a highly critical eye before you start dismantling your existing supply chains. We leave it to you, the listener, to form your own conclusion. Navigating the transition from traditional to agile manufacturing is a complex, ongoing challenge, and there is certainly more to explore beneath the surface. Until next time, keep asking the hard questions.